Alright, hello class. This video is to show how to do some of the structures that was on assignment 3 in the Chem 140 class. It's important that you learn how to use ChemDraw, and I know that looking at some of the structures that you drew, they looked correct, but were counted incorrectly because the proper procedures were not followed for drawing the structure. So I thought I would pick some of those out and do those and record it so you can see how to do the structure. So first of all, you got to read the problem. It says click the draw structure to launch the drawing utility. This sulfur hexafluoride molecule has an expanded octet, so you know it's going to have more than 8 electrons around the central atom sulfur, and they want you to draw a Lewis structure. So you click on draw structure, and you should get a palette that looks like this. If it doesn't pop up, maybe you have your pop-up blocker on. If you have some problems with this, again, maybe your computer's not up to snuff as far as compatibility. If your JavaScript's not up, that's going to cause a problem with this as well. Now, I've talked about that you can start this with a single bond if you want. So it doesn't matter. You can start with a bond if you like, and you can put a bond like so. And then we're going to click A to represent the element. So you see the blue box, that's the crucial part. That blue box must be shown, and then click on that, and that'll and then put the sulfur in. Now the reason why that's so important is that it tells us that the sulfur is bonded to that, is stuck to that bond, and if the blue box isn't there, you could be off to the side and it looks like the sulfur is bonded to it, but it's not actually attached. And when ChemDraw goes to grade this, it's going to grade that incorrectly. All right, so next thing is you could highlight the blue box here if you wanted to, and you could put in a fluorine if you want to do that. All right. And then maybe you want to click in and do another sulfur bond. So, or another bond. So watch this. I highlight the sulfur, and let's just go on and put all our bonds in. I want to put this one in. And somebody asked, does it matter, how you angle them? For this, it does not, because it's not asking you for VSEPR. It's just asking you for the structure. So we do something like, I would try to line that one up. Something like that. So that shows that there are a total of 6 bonds coming off of the sulfur. Let's click the symbol for text and highlight. Make sure the blue box is highlighted. Let's put in another fluorine. Same thing here. Blue box is highlighted. Another fluorine. Blue box is highlighted. Another fluorine. Blue box is highlighted. Another fluorine. And blue box is highlighted, another fluorine. All right. So we've got our 6 fluorines attached to the sulfur. Now, at this point, you might want to calculate the total number of valence electrons you have to work with. So sulfur is in group 16. It has 6 valence electrons. Fluorine is in group 17. It has 7 valence electrons. So 7 times 6 is 42. 42 plus 6 is 48. So we got 48 electrons to deal with, and right now we've used a total of 2 times 6 bonds here. 2 times 6 is 12. So we still got 30 to do. So let's click on lone pair of electrons here. Now watch what you do here. You just highlight the fluorine and go 1, 2, 3. All right? Does it for you. Highlight the fluorine. 1, 2, 3. Same thing with this fluorine. 1, 2, 3. Same thing with this fluorine. 1, 2, 3. 1, 2, 3. 1, 2, 3. All right, so when we do that, each one of the fluorines feels like it has 8 electrons, and 8 times 6 is 48. Oops, did I make a mistake here? 7 times 6, 42 plus 6, yeah, 48. 48 electrons. So this is 48, all right? So once you're satisfied with that, you can click Save and Exit. All right, so there's my structure. And then I can check my work, and it says, good job, correct. All right, so that's the process. Let's look at another one. There was a couple more that seemed to be problematic. So 47 was one of them. Well, maybe I should do it this way. Just click. Yeah, I probably should have. I had them written down at work, and I'm actually doing this at home. All right, so here's a good one. Here's another one that was some problems. All right, it says, is sulfur dioxide a polar or nonpolar covalent compound? Draw the Lewis structure to prove your answer. All right, so we're going to click on this. I'm going to try something a little different here. So this is what I would expect students to do. I would expect them to maybe even click on A first. We'll put it right here at the sulfur. And then you'd click on, I think most students, what they would do is they'd highlight the sulfur like so, pull out a bond this way, and pull out a bond this way. And they click on A again, they put an oxygen here, and they click on oxygen here. And then they would click on lone pairs, and they would go 1, 2, 3. Click on this oxygen, 1, 2, 3. And then they click on the sulfur and go 1, 2. All right, so they'd have a structure that looks like this. All right, so if we do that, what I want you to do is count the total number of valence electrons in this structure. So you've got 8 around the oxygen. There's 2, 4, 6, and then the bond. That's 8. Same thing on this side. So that's 16. And then you got to add the lone pair here and the lone pair here, and that's 20. All right, so I got 20 valence electrons. So here's the question. Is that correct? Should I have 20 or should I have more or less than that? Well, you got to go back over to the molecule itself. It's sulfur dioxide. Sulfur's in group 16. It has 6 valence electrons. Oxygen's in group 16. It has 6. So 6 times 2 is 12 plus 6 is 18. So there we go. 18. All right. We got 20. So what does that mean? Well, I need to erase a pair. So I'm going to erase a pair right here. Okay. So I do that, and I go, okay, now sulfur only has 6. So then you go, what if we erase this bond here? All right. And instead of having that, we're going to put in a double bond. So you highlight that, highlight the sulfur, go like that. And now, one of the things that's a problem here is the... you shouldn't have, now you got too many electrons on the oxygen, so let's take the eraser and erase that. All right, and this hydrogen doesn't look right. Now, I did notice this glitch here, and so you erase that and you get something like that and you go, oh, I really messed it up. All right, so take the text again, put that in, and let's put in a S for sulfur. And then let's click off of that just to see what we got here. All right. So, is that a proper Lewis structure? Well, it's 2, 4, 6, 8 on the oxygen. It's 2, 4, 6, 8 on the sulfur. And it's 2, 4, 6, 8 on this oxygen. So it looks right, even though there's these boxes saying what an atom in this label has invalid valence. No, it's got right. 2, 4, 6, 8. So it looks right to me. So that's one thing, we could do that. Now, here's where we get into a little bit of a problem too. If this is the correct structure and it's linear, you might be saying, well, this is more electronegative, pulls the electrons out this way, and the electrons are pulled out this way with this oxygen. They cancel each other out, and you say it's a nonpolar molecule. But let's look at this closely. Here's the A. In VSEPR, this is an X here, this double bond, and this is an X here, this single bond. So really, this is AX2E. So AX2E, there's really 3 things coming off the central atom. So how do you keep 3 things as far away from each other as possible? You put them in the corners of a triangle. So let's see if I can, I think it's, Yeah, it's not that. Let's see. There was a way to pull these, and I don't know if I can do that. No, that's doing that. It's not helping me. All right, so let's first of all, let's erase that. All right. So no, that's not helping me. All right, so what am I going to do here? I can't remember how you manipulate this. Can you go like that? No. All right, so let's just erase it and start over. Since I don't remember what you do here for that. Oh, that's not helping me. All right, so let's just reset. So you can do that. All right. Do you guys prevent that? All right. So let's go with the sulfur again. We'll put it right here. Put the S in for sulfur. All right. Now, we know on this sulfur there is a lone pair. So let's just go and put that on there. So we know that now. Let's just do that like that. All right. All right. And we know there's a double bond. So watch what happens here, though. I'm going to put the double bond in the corner like that. All right. And then we know it's a single bond on the other one. So highlight the sulfur, pull it down like that. All right. And then we know there's oxygen attached here. Oops. Now, see, there was a problem. I saw it as soon as I did it. I know there's an oxygen attached here. There should be a blue box show up. There we go. And let's do it on the other side. Blue box shows up. Put an O there. All right. And then let's put in our lone pairs around this. So 2 lone pairs on this oxygen. 3 lone pairs on this oxygen. All right. And let's save that. There's something that looks problematic. The sulfur's not showing. Let's see what it looks like when I say edit structure. Is there a problem here? It looks like we've got a problem because it didn't show up here, right? So let's try it again. A goes here. Let's put a sulfur. All right. Double bond off the sulfur, so let's highlight that, make sure blue box pull out. Single bond off the sulfur, highlight the sulfur, pull out. All right. Oxygens, let's put the oxygens on here. 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 And then we'll start putting in the lone pairs. 1, 2, and 1, 2, 3. And then let's get rid of the hydrogen. Or let's do this. Wait, before we do that, let's highlight this. And that. Okay, and then let's get rid of the hydrogen. Yeah, I was afraid of that. All right, so let's do that. Put a sulfur in. All right, so let's hit save and exit. So we get something that looks like that. Now that looks more like it. Is it polar or non-polar now? Well, this is pulling down. This is pulling down. Overall, there's a resultant vector force down this way. So let's say polar. And let's hit check my work. And we've got a correct answer. And so that's what you have to do. Now, I agree this one looked harder. There's some manipulation there. Do you have to make it angled like that? Not to get the correct answer, because it doesn't ask you for VSEPR. It just says Lewis structure. Let's see what theirs looks like. We can actually see the answer, right? Show me. Let's say we give up and see what it looks like. All right, so that's what theirs looks like. But you know what's nice about this? You get 3 attempts. You could see this. Theirs is nice and linear. That's fine for a Lewis structure. You can show it as linear. There's no problem. But what I want you to remember, this is A. X is this double bond. X is this single bond. And this lone pair is an E. So this is AX2E. The book doesn't do a real great job saying it that way, AX2E. What they will say is bonding, bonding, non-bonding. So you got three things coming off the central atom, and that's going to make it go into the corner. Each one of these things coming off goes into the corner of a triangle. One of them is this lone pair, so it looks invisible. So what we actually get is we get that bent geometry. That's what that's called, bent. All right, just trying to see. So that's what it looks like. All right. Let's move on. Let's see if I can find another one that gave people problems. That was one it did, and maybe it's because it's a little, you get that hydrogen, you try to say, what am I supposed to do with that? You need to get rid of it. That could have been a problem. What I would also suggest here is that when you're doing these Lewis structures, I would highly suggest that you write it out on paper first, work it all out, calculate your total number of valence electrons, write it out on paper, and then when you're ready, just maybe do them all and then get online, pop them in. I think that works better than just sitting at the computer and trying to flip it around and so forth. At least have something in, because it's when you got it in paper, I feel like you can, you've got a better, you're centered to it, and you're not as likely to make a mistake. All right, so here's one. I don't know if this is the one people missed, but this is what I did see happen. So on this one it says, using Lewis structures and VSEPR, valence shell electron pair repulsion theory, which says that lone pairs are the most repulsive. They want the most space. They want to be as far away from each other as possible. Then bonding pairs are next. They want to be as far away from each other as possible, but they don't have as strong as repulsion as lone pairs. So it helps us determine what the three-dimensional geometry is. And it's such a great theory because it works off Lewis structures. You write the Lewis structure correctly, and then looking at the central atom and looking at the types of pairs of electrons coming off the central atom, you determine a three-dimensional geometry. All right. So what does that look like? Draw structure. You would click this. Now, I think what I saw happen here, this was one people missed. I'll show you what I saw. I saw people, and then I'll erase it and show you what you probably you should do to get the right answer. So they drew a bond like that, and then they said, okay, I'm going to connect the nitrogen here. And then I'm going to take a single bond, and I'm going to put, so highlight the blue, pull the nitrogen down here, pull another one here, and then they click here, and they go, what am I doing? What am I doing? Thinking about the other. All right, let's go back up here. Let's make it a H. And, yeah, all right, that looks better. And then an H here. All right. All right, so we got the three hydrogens attached, and then we're going to attach this right here, like so. Okay. So you go, oh, there's my Lewis structure. Each hydrogen has one valence electron. Nitrogen has 5. So it's a total of 8 valence electrons. There's 2, there's 4, there's 6. So it looks like a good structure. All right. So what do you think? Is it polar or non-polar? Polar, because there's nothing canceling this. Like, we know nitrogen's more electronegative, so the electrons are pulling this way. And you'd say, well, these cancel each other out maybe, and this one's then not canceled out or something. And then so you'd say, because this one's not got a counterbalance, right? So you probably say it's polar. All right. So let's save and exit, and let's hit polar. All right, so it looks good, and you're saying, oh, I've got the right answer, so I'm going to hit check my work, and it says correct. Oh, so that's good. Now, let me do something else with this. If I was drawing this structure, and I wanted to, show the VSEPR, I probably would click the A here and put a nitrogen. And then I probably would. I take the bonds here, and you could pull one down like this, and then pull one like that, and then pull one like that, and then attach the hydrogens to it. So hydrogen, 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 and then put a lone pair on the nitrogen. So highlight this and go like that. Now you go, why would you do that? Well, this shows the VSEPR of it. It's AX, so we got a total of 8 electrons. It's AX3E. So there's an X, there's an X, and there's an X. 3 bonding pairs. So 3 bonding pairs and a lone pair. So it's AX3E. How do you keep 4 things as far away from each other as possible? Well, it's a tetrahedral framework. It's how, you know, you'd say, okay, generally the way I keep 4 things as far away from each other as possible is like a cross, like this little, I don't know if you see this marker here. I'm going to assume that you do, but it's a cross. Well, the angle, though, between the horizontal and vertical bars there is only 90 degrees. In a true tetrahedral, the angle between, if there's a hydrogen here to this nitrogen to this hydrogen here, it'd be 109.5. It'd be greater than 90 degrees. So that's better because it keeps the electrons further from each other. So this is, so it's a tetrahedral framework. Now, when we go to describe this geometry, you always describe geometry by what you see here, this part. So we would call this trigonal. Trigonal means 3. Pyramid. Trigonal pyramidal or trigonal pyramid. If you say trigonal pyramidal, you're using 2 adjectives. If you want to end in a noun, you'd say trigonal pyramid. All right? So that's what the structure would look like. We'd save and exit. Got a nice structure over there. We know it's polar. We're going to check my work. There we go. So what I would do is, if it's asking for VSPR, I would take on a structure similar to this instead of the T-shape. Still works, the T-shape. They give you credit for it for this one. But I feel like there's one I saw that they don't quite give you credit if you do it just Lewis, and it, because it's stressing the VSEPR theory. All right. I don't know. I think this one, it's tetrahedral and it's nonpolar. Let's see. I want to do one more, and then I think we'll call it a day. It's not that one. Most people got that one right. The carbon disulfide. They did fine. Yeah. Yeah, this one. Let's do this one. So we have methanol here. Methanol. All right. So we're going to draw the structure for that. All right. So you could start with a bond, or again, I did find out you could start with A. You could start right here and put a carbon. All right. And then we're going to go single bonds. So we know the carbon's bonded to 3 hydrogen there. And then it's bonded to an oxygen. All right. So you go, how do I know that? Well, okay, carbon. Let's do a couple of things here. Let's look at the compound, and let's think about it. Carbon's in group 14. How many valence electrons does it have? 4. So it would like to bond 4 times. So it's going to bond to these 3 hydrogen. That's 3 bonds, and then the oxygen. That's its 4th bond. And then this oxygen is going to be bonded to the hydrogen. So at this point, what I want to do is just click on this, and let's put in your hydrogens. Again, the key here, make sure that blue box shows up, because I think that's where you're missing it. I think some of you are like dropping it down here, and it's going to look right, but it's not attached to the carbon. It's got to show the blue box. So let's do that. Oops, I got fancy. Didn't see that. Let's go back up here. Let's delete that. What's going on? I think I've really messed it up. All right. Oh, it doesn't look bad. All right. So let's click this one. Let's put the oxygen in. All right. So now we got another bond, right? We got to get another bond and stick that from here to the hydrogen, all right? And then we know there's got to be a hydrogen at the end of this. So let's put one right there. Okay. All right. So what's left? Well, you know there's one bond on everything. So, well, you at least know that. That's the structure. So what you want to do right now is make sure your total number of valence electrons is working. Can you see an element here that is not following the octet rule, is not satisfied? Well, the hydrogens don't follow the octet rule because they only need 2 electrons. So the hydrogens are all satisfied. The carbon is satisfied. It's got 8 electrons around it. What's not satisfied is the oxygen. All right, so do we have electrons that we need to add to make the oxygen satisfied? Well, how do we know? Well, you have to come over here and look at the structure. There's 4 valence electrons for carbon. There is 6 valence electrons for oxygen. That's 10. And then 10 plus 4 is 14. So we got 2, 4, 6, 8, 10. So we got 4 electrons to add, or 2 pairs. So let's do this, 2 pairs. So you go to the oxygen, make sure it's highlighted in blue. That's the key right there. 1, just click, and that puts that. Click again, puts another one there. All right. So there is my Lewis structure for methanol. I'm going to save that, and then I'm going to check my work. There we go. All right. I can do more. I just hope you feel comfortable with ChemDraw. To me, it's been a great program. I know there was a quirk there on that sulfur dioxide. We still had some red boxes, but the structure's right. And I know as a student you're looking at that and going, saying it's not right, but according to what I've seen in the book, this is what it looks like. In fact, that one's done in the book. It allows you to draw a structure. Just think about it. I'm teaching a class of 30, and for me to go through and try to grade every one of those by hand, it'd take forever. And you wouldn't get the feedback in a reasonable amount of time before a quiz especially. Yeah, you get it back probably before the exam, like we're doing here, but you wouldn't get it back before the quiz. And so that's what's so great about it. You get that feedback instantly. You get up to 3 times. If you do the structure wrong, it tells you that you're doing the structure wrong. And so that gives you some help. And you can refer back to the book and get the answer. What I don't like is I don't like it when a student's frustrated because it looks right and they think it's right and it looks right and it counts it wrong. And then so all I can do is reconstruct it and see if it counts mine right. And if it counts mine right, then I assume that it can be done right and that something on yours is not attached. And we can see it's easily done, right? If the blue box doesn't highlight and you're outside of that and you click an H, it looks like it might be attached to the line, to the bond, but it's not. So I understand that frustration. I hope you'll focus on that. And if there is some that's giving you a real problem, just email me and I'll either do a video or I'll do it and then kind of tell you what I think is the key to it. Again, the sulfur dioxide is a little quirky there, and it probably should run better than that. And I think the reason why it is a little quirky is if we used an expanded octet, you would have had sulfur, then 2 double bonds coming off, and then you would have had a lone pair on the sulfur. When that gives sulfur too many, it gives it a total of 10 instead of 8. But when we start looking at formal charge, that's a valid structure. Sulfur with 2 double bonds coming off to the oxygens. So I think there is a little quirkiness there, but if you'll do it like you saw it in the book, like it should be done, and then you saved an exit, you would have gotten the correct answer there. All right. I hope this helps you. If it doesn't, let me know. I will try to turn another video for you between now and midterm exam, because I want you to do well. And I hope you are studying for the midterm exam right now, because it's coming up, and it's over a lot of material, but that's the way the nature of the online class is. We're only allowed to give 2 proctored exams in a semester, and I've argued against that, but that's what we have to do, and so we have to work within the guidelines of KCTCS. All right, thank you, and again, keep in contact, and again, let me know if you need help.